Hello. Do you remember where we had left our last lecture? Or what had we done in our last lecture? We did closed interval, open interval, some combination of those intervals like semi-closed or semi-open. But while defining closed interval or open interval, what word I had used? I used word collection of numbers. Very intelligently, I had not used word set. And word set is an extremely important term in mathematics. So today in this lecture, we are going to take only basics of set theory. Now realize one thing, that even if I say sets, the entire set theory we are not going to take here, only that part which is required to understand basic algebra. Now, when I say all this, you have understood that there is some slight difference between word set and collection. Now, I say set is a well-defined collection. Now, what I mean by well-defined? Now, if I say set of animals, then a rat may come or even a leopard may come. And you realize that, oh, I didn't want leopard in this. I wanted only rat. Means what? That we are looking for only pet animals, not wild animals. If you say wild animals, then perhaps like a leopard may come or elephant may come. Elephant and rat will not go together. Now, when you say pet animals, then only like cow or maybe goat or rat may appear there. Realize this, those words pet and wild have made the collection as a well-defined collection. So a set is a well-defined collection. So the moment we use this term in mathematics, word set would be used judiciously, not anywhere and everywhere. Now, if you want to say that I want 2 by 3 or 1 by 2, that means we are talking about rational numbers. If I say that I want -3 or -2, or indirectly I am saying that something which is in the form of p by q, I do not want, means you are talking about integers. So those words integers or rational numbers are making those sets the precise collections, well-defined collections. So in mathematics, when we use word set, we are very precise that where we are going to use that word set. Did you notice when I say -3 is an integer, indirectly I am saying that -3 belongs to set of integers, or it would be called member of that set. Mathematical term for this is element. So an element is a member of that set. Now, can we look for more examples like what we have learned from there? We have learned closed interval, open interval. Can't we look at them as sets? In fact, we have defined them as sets. So a closed interval is a set, and every element of that closed interval would be an element of that set. Now let us take one example. I have taken 2, 7, a closed interval. Now you can pick up any element from that interval. I have just mentioned 3 as an example, and I have used 3 belongs to 2, 7. Now belongs to I have denoted by epsilon notation. So epsilon stands for belongs to. Now if I want that so and so element does not belong to that set, obviously there has to be some notation for that also. There should be some notation for an element does not belong to that set. For example, if I have to say that 8 does not belong to interval 2, 7, then it would be outside that set. So 3 belongs to that 2, 7 interval we have shown on number line, and now I may write 8 does not belong to. Would you like to write all the time does not belong to so and so set? Instead of that, let us have a notation for that. So when I say x does not belong to, you are intuitively right. We are going to write it as not by slash, how we had written for not equal to. Same way we are here writing x does not belong to a by writing that slash over epsilon. Now, take one example of does not belong to. Remember open interval, we had mentioned that endpoints are not included in the set. So I take one example as -2, 1, suppose some open interval, and I can very well claim that -2 does not belong to that set. Now, I just wanted to emphasize that how do we write belongs to by epsilon? How do we write does not belong to by showing epsilon and slash in this particular part. Let us move further. Let us take some operations on sets. Now, since we have defined term set, we expect some mathematical operations also. So we have taken only those operations which are immediately required. There could be some more operations also. So we take two. One is union and other is intersection. Now let us define them first. Union of A and B, we denote it as AUB, and it is defined as it is collection of all those X, and then I will say the property, and the property makes it more precise and hence it becomes a set. What type of X you are going to choose, which are in A or in B. So OR makes it a particular set. The definition of A intersection B is that it would be a set containing all such X which are in A and B. Means only those elements which are common to A and B. Now since we have taken closed interval, open interval already, we have seen them, we have learned them. So let us take some examples from there to understand that how we will be writing A union B or A intersection B. Because once you understand that how to write A union B, A intersection B, it would be easier for us in our further lectures to write further precise statements. So I have claimed here that if A is closed interval -3 to 5 and B is 2 to 7, then A union B, I claim it is -3 to 7 and A intersection B, I claim it is 2 to 5. How do I say so? We can actually plot them on number line. Mark -3 and 5 and also 2 and 7. And now what we realize that -3 to 5 is our set A and 2 to 7 is our set B. And we want now to write A union B. So elements which are in A but not in B can be taken. Elements which are in B but not in A can be taken. So obviously we are looking for something like -3 to 7 and that would be our A union B. Now for A intersection B, we want only the common ones, and from where to where it will lie? That would be from 2 to 5. So A intersection B is 2 to 5. So the common ones are written in A intersection B and the extra ones which are in A but not in B or which are in B not in A, they are to be included in A union B. Now once you understand these two terms clearly, our further sessions would be more easier. Now let us move further to types of sets. Again, as I said, all operations we are not taking here. Same way I would be saying that not all types we will be taking. There would be many more types of sets, but we will be taking only two. One is singleton set and other would be null set. As name suggests, singleton set means which has only one element and null set means the one which does not have any element in it. Now, do we have any precise notation for it? Then of course singleton set means those two curly brackets and element written inside. And what about null set? Null set means you just write curly brackets. Do not write anything else inside. Means there is no element in it. Or instead of curly two brackets, we also have another notation which is called phi. That phi may be a new symbol to you. So if you wish, you can continue with phi, or if you wish, you can just write it as two curly brackets. So I have given here one example where I have taken one set which is only set of all even integers, and set B I have considered which is all set of odd integers. Now what would be A intersection B? It is phi, because which is an even integer cannot be odd integer and the one which is odd integer cannot be even integer. Means there is nothing common between those two sets. And for A intersection B, we write only the common ones. So it is phi, and so it turns out to be nothing but null set. So I actually here in this example, I tried that whatever we have learned just now, intersection, that we can combine with null set. I think for this session, this is good enough. And when we meet next time, that would be another session. And if anyone is looking for something more on sets, it would be covered under separate session called sets relations function. Thank you. Stay tuned.